Hello, my name is Ethan Lee, and today I'll be going over the second part of my Intro to Competitive Programming video series, I guess. Okay, so today I'm going to be going over a few different parts of competitive programming that are kind of all over the place. So allow me to talk a little bit about what I'm going to talk about. First, I'll answer why CP or competitive programming is difficult to begin with. Like what makes solving a problem so hard. There's also the idea of time complexity or runtime complexity, as well as a little bit about data structures and algorithms, as well as problem solving strategies. And finally, I'm just going to talk about how competitive programming is a very broad field, surprisingly. Okay, so first, let's talk about what makes competitive programming difficult to begin with. Because technically speaking, for example, if you wanted to, say, find the shortest distance between two different points, like for example, my house to the nearest gas station, technically speaking, couldn't I just try every possibility? Couldn't I be like, oh, I'm going to go to my house and then fly to China and then find the nearest gas station there? And I'll consider that strategy and then the other strategy, and I'll try everything and I'll find my answer. Well, the issue is that in competitive programming, there are always time and memory limits. So, as I just mentioned, any problem can be solved if you brute force it or try every possibility. However, solving problems with time and memory limits means that you need to optimize. Because if you try to consider every possibility, more often than not, this will take a very long time. Even outside of competitive programming, it's important to try to minimize the time and the memory that you spend in order to complete a specific task. And so that's why competitive programming has these sorts of seemingly arbitrary limits, which makes it much more difficult to solve a problem that may seem easy on the surface. So now that I've talked about time and memory limits, let's go over what exactly they apply to in competitive programming. How are they applied, and how people measure their own programs against these limits. Memory limits are pretty self-explanatory. Just don't go over the memory that they limit you to. But time limits are actually a little bit more complex. And this is where runtime complexity or just time complexity comes in. Now, if you ever look at competitive programming algorithms, you might notice that like next to the algorithm or next to whatever you see, you might see a capital letter O and then parentheses and then a bunch of random letters. Those letters also being in the competitive programming problem that you're reading. So for instance, O of n or O of log n. So what does this mean? Now, what you're seeing is an example of big O notation. And essentially what it's doing here is trying to see how fast your code runs in terms of the data, or the size of the data or the size of the input you're given. So, for example, if you look at O of n, what this basically means is that given an input size of n, the worst case scenario, the longest that the algorithm will run, the biggest number of calculations that the algorithm will have to complete is exactly n. If you have log n, that basically means it'll take, well, at most log n calculations. So for example, linear search is O of n, and binary search is O of log n. In other words, if you have code that runs in O(n) time, it'll basically take n calculations at worst in order to give you your answer. Now, to run this back to the time limits that I was talking about earlier, a general rule of thumb is that if you have a certain time complexity and you substitute n given in the problem, so for example, if you have 100,000 numbers and you substitute that in for n, and the resulting number is less than about 10 million, you will pass. Now, I understand that this may be a little bit difficult to understand because I don't have a problem in front of me, but rest assured, this is very important. And if you do more competitive programming, this will make a lot more sense. Okay, so now that I've talked about time complexity, I can talk a little bit more about data structures and algorithms, both of which are measured due to their time complexity. So data structures and algorithms, what exactly are they? Surprisingly, they're not the same thing, even though they're stuck together a lot. Data structures can be very advanced. They support operations in a certain time complexity. So for example, an example of a data structure could be a stack or a segment tree as seen on screen. So I'll talk a little bit more about a stack on the next slide. Now, algorithms are not the same as data structures. They don't exactly store data. They complete a specific task. So for example, it doesn't show on screen, but the single source shortest path algorithm, which essentially finds the shortest distance between 2 points, is an algorithm because it does a very specific task, that is finding the shortest distance between 2 points. I'll be going over an example of an algorithm as well. So, as I mentioned before, let's take an example of a data structure, that being a stack. Now, a stack is basically just like a stack of paper or a stack of anything. What comes in first will also come out first, and this happens instantly. For example, let's say that I have a stack that has the number 1 in it, and then I want to push 2 to the stack. Basically, what would happen is that 2 would go on top of 1, and then later, when I wanted to pop the top element from the stack, 2 would come out. So that's basically how a stack works, like a stack of paper again. If I put something onto the stack, the first thing that I take out will be the last thing that I put in. So first in, last out. Never mind what it says on screen. It's first in, last out. So in other words, the stack supports 2 specific operations. You can add to the top of the stack in O1 time. See, there's the time complexity we were talking about earlier. And you can remove from the top of the stack in O1 time as well. So notice how that I specifically described the 2 things a stack can do and mentioned the time complexity it takes to do those operations. That is an example of how to describe a specific data structure. Every data structure, all of the data structures in the world, can be described in terms of these operations and their specific time complexities. So that's an example of a data structure. Now, let's talk about an example algorithm, that being binary search. So have you ever looked through a dictionary? You definitely didn't just skim from beginning to end looking for the word you were trying to find. Instead, what you probably did was start from the middle of the book and then look at the left or the right based on what word you were looking for. Binary search uses this strategy to to search a list that is already sorted. It starts from the middle and then changes the bounds and goes left or right based on what you are looking for. So that might not make much sense when I'm saying it like that, but let's go through an example. Let's say we have the sorted list 1, 2, 3, 4, 5, 6, 7, and I'm looking for element 6. So what I would do is first I would have to look at the entire array. So I would set my left bound to 1 and my right bound to 7. Then I would look at the middle of the 2 boundaries, that being 4. So since 4 is not 6 and 4 is less than 6, we know that anything behind 4, so 3, 2, and 1, in other words, anything that is to the left of the middle definitely cannot be what we're looking for. Therefore, we can move our left boundary up to the middle point that we just found. So now we're looking between 5 and 7 for 6. And then we look at the middle again and we see 6. Since 6 is 6, we terminate. So this is basically an example of an algorithm. So a very specific set of instructions that, given a very specific set of data, will always return a specific result. Algorithms are really just one-trick ponies most of the time, but that's what makes them powerful. All you really need to do is memorize an algorithm that you're looking for and apply it to the right situation, and you're golden. And finally, let's take a look at something that's not a data structure or an algorithm, because it wasn't confusing enough already. So there are a few problem-solving strategies that you can apply to some competitive programming problems. So an example of this is the greedy strategy. So an example of a greedy algorithm is an algorithm that applies the greedy problem-solving strategy in order to solve a problem. So basically what the greedy strategy is you take the best possible solution that's right in front of you repeatedly, and you make absolutely no consideration for the final answer or for what's 5 steps in front of you. So for example, if I'm just playing video games instead of recording this video, that would be an example of a greedy strategy applied to life. There's also divide and conquer, which is exactly what it sounds like. Now, to recap what I just said, there are data structures, there are algorithms, and there are problem-solving strategies. All 3 of these can be applied to competitive programming and other computer science problems in order to get what you want. Okay, now you might be thinking, what else is there to learn? What else is there besides the stack or the binary search that I just described? Well, competitive programming is surprisingly deep. There is a lot of different things that you can learn for general informatics. So for example, there are many different data structures with different operations with different time complexities. There are the segment trees or seg trees that I described earlier. There's priority queues, there's binary trees, etc. There's a lot more. There's also many different algorithms with their own specific goals. Like for example, the shortest path algorithm, there's flood fill, and more. And there are also a lot of problem-solving strategies that I probably couldn't fit on this slide. So if all of this sounds intimidating, that's because it partially is. But remember, there are always resources. There's always online websites like usacode.guide. There's also your computer science teacher, as well as computer science organizations or clubs in your area. So if you are interested in learning about these data structures, these algorithms, and these problem-solving strategies, there are different places where you can look besides this 15-minute video. So I wish you luck. Thank you.